All right, we're going to review simple machines. Before we get started, I do want to remind you that if you go to Schoology, under Principles of Engineering, you have the Resources folder. In the Resource folder, you have your engineering formula sheet. And if you open that up, you can scroll down. So all these formulas are on that reference page, and you may use that reference page on tests, so you don't have to memorize the formulas. We just have to be able to apply them. All right, so the first thing we want to look at is the ideal mechanical advantage. This is if there was, no friction from movement or anything. This is just the purely theoretical value. And if we look at it, the ideal mechanical advantage is just the distance traveled by the effort divided by the distance traveled by the resistance force. Then the actual mechanical advantage, we get that by measuring. So we know exactly what our applied force is, exactly what our resistance force is, and that's going to give us our actual mechanical advantage. But we do have to measure that. That's not something we can get theoretically. All right, with the first class lever. The first class lever can have a mechanical advantage of 1. And that would be this situation right here where the pivot point is right in the center. And so your effort and resistance would be the same. So take 5 pounds of effort to lift 5 pounds of resistance. Now here we've shifted the pivot point over to the side, and if our resistance is on the longer arm, it has a mechanical advantage of less than 1. That means it's going to take more effort to lift that than the resistance is. So it might take 10 pounds of effort to lift 5 pounds of resistance. On the other hand, if we put our effort on the long end and our resistance on the short end, it's going to have a mechanical advantage of greater than 1. So in other words, it'll take less effort to lift the weight. All right, now the second class lever, our resistance is between the pivot point and the effort. Okay, this one will always have mechanical advantage of greater than 1. It doesn't matter where we put it along there. The closer it is to the pivot point, the greater the mechanical advantage, but it's always going to have a mechanical advantage of greater than 1. Then if we go to a third class lever, where we have the resistance way out here on the outside and we're lifting in the middle, that's always going to have a mechanical advantage of less than 1. It's going to take more effort to lift the resistance. So it may take 10 pounds of effort to lift 5 pounds of resistance. And again, that will depend on where along that lever you are. All right, so if we look at our moment, it's our distance times force. And then the torque is a force that produces a rotation or torsion. All right, so let's look at calculating the moment for this lever. Again, our moment is distance times force. So our distance is 5.5 inches. Our force is 15 pounds of effort. So if we multiply those together, we get 82.5 pounds. All right, now we can take that moment, that 82.5 pounds, and calculate the resistance. Okay, so this would be our actual mechanical advantage. here if we're actually putting 15 pounds of effort. So we take our moment for the left side, which is 82.5 inch-pounds. Now over here we're lifting 36 2/3 pounds. So we need to find this distance right here. And so go back to your algebra. To get the distance by itself, we divide both sides by the 36.66 or 36.67. If you're using a calculator, you can be more accurate and just put in 36 2/3. And we get about 2.25 inches. So that would be our distance right here. All right, so our ideal mechanical advantage, again, is going to be our effort divided by our resistance. And it doesn't matter if we're using a lever or a wheel. A wheel is just a lever that's inside of a circle. Okay, and the way that works, if we've got the 2 pi, when we divide it, the 2 pi cancels out. Okay, so it doesn't matter if we're dealing with a wheel and axle or a lever. The equation's still exactly the same. All right, so to find our actual mechanical advantage, we take our AMA of 32 pounds, that's our resistance, divided by our effort. So it's 2 to 1. Okay, the IMA, now in this one we're just looking at the distances. So we've got the 5.5 effort divided by 2.25, and we get 2.44 to 1. All right, so again, our actual mechanical advantage is always going to be lower than the ideal. Part of it could be the weight of the beam that we're using. It could be friction. There are a lot of things that can cause it to be a little bit different, but none of our machines are 100% efficient, so the actual mechanical advantage is always going to be somewhat lower than our ideal mechanical advantage. Okay, our percent efficiency is just our actual mechanical advantage divided by the ideal mechanical advantage. Then we multiply that by 100 to change it to a percent. So we're going to take our 2.1 divided by 2.44. I'm sorry, we're just going to do 2 divided by 2.44 times 100, and we get 82%. Now, if we ever get over 100%, then you'll know that you've got it upside down, and you put the ideal mechanical advantage on top. All right, we've already mentioned that no machine is 100% efficient. Wheel and axle is the same thing. Now, we're looking at the diameter. So again, it's our effort divided by resistance. And all these, it's always going to be effort divided by resistance. So the IMA of the wheel and axle, that's going to be 6 inches divided by 20 inches, which comes out to 0.3. Now we could write that as 0.3 to 1 or 0.3 to 1, or it's more common. We don't want to have a leading decimal in the first number, so we just say that's 3 to 10. Okay, but 0.3 to 1 and 3 to 10 are the same thing. We just multiply both sides times 10. Okay, now if we flip that around and it's the wheel driving the axle, say you're coasting down a hill or something and it's the actual wheel driving the axle, that'll be 20 divided by 6, which is 3.33 to 1. All right, now let's look at the actual mechanical advantage. Okay, this is going to be the resistance force over the resistance effort. And again, we have to know those values. So on this one, it's going to be, if the wheel is driving the axle, it's going to be 200 divided by 70, which equals 2.86 to 1. And then if we reverse that, it's just going to be, the efficiency is going to be our actual mechanical advantage divided by the ideal mechanical advantage times 100. So that's going to be 2.86 divided by, and then the 3.33 that we came up with earlier, times 100, which comes out to 85.9%. Now with pulleys, we just have to count the number of lines coming off a moving pulley. If the pulley is not moving, then the mechanical advantage is, there's not going to be any mechanical advantage. So if we look at this pulley here on the right, it's a fixed pulley, so all we're doing is just changing the direction of effort. Now, it might be easier to lift 10 pounds if you grab a rope and you pull down because you can use your body weight to help lift it, but there's really no mechanical advantage right there. But on this one, you can see the pulley's moving, so this beam is holding up half the weight, and we're lifting half the weight. So to lift the 10 pounds, it only takes 5 pounds of effort to move it. So we're just counting the lines coming off the moving pulleys. All right, so we're going to lift a 600-pound motorcycle right here. All right. We're counting our moving pulleys. These two pulleys are moving. These two pulleys are fixed. So I count the lines here. I've got 1, 2, 3, 4. I don't count this line right here because all it's doing is just changing directions. Okay, so the ideal mechanical advantage of this system, again, we count the lines coming off the moving pulleys. There's 4 of them. And then to calculate the actual mechanical advantage, we'd have to see how much force we're using right here. You know, is it 630 pounds, 650, or whatever. And a lot of it would depend on how resistant the bearings are in these pulleys, but they're not asking us that, so we'll move on. The inclined plane. Again, ideal mechanical advantage is the distance of effort divided by the distance of resistance. Okay, so the distance effort is the length right here. And the distance of effort is how high we're moving it. Okay, so the IMA is the length, that's the slope, that's whatever you're going up, divided by the height. So if we're looking for the ideal mechanical advantage of this inclined plane, we take the effort, the 15, divided by the 4, and we get 3.75 to 1, or if we round it off, 3.8 to 1. Okay? And that should be approximately right there, not equals. So. All right, now we're going to look at the actual mechanical advantage of the inclined plane. We've got 50 pounds in our little wagon right here, and it just takes 20 pounds of effort to move it up the inclined plane. So it's 50 divided by 20, which is 2.5, so we come out with 2.5 to 1. So now if we want to look at the efficiency, it's going to be our 2.5 divided by the 3.75 or 3.8 that we came up with earlier. Then we multiply that times 100 to change it to a percent, and we get 67% efficient. All right, now with our wedge, our ideal mechanical advantage is our distance of effort divided by our distance of resistance. So our effort is the length. Okay, it's the length right here. And we take the total length. We don't take the length of this side of the angle. We take the length from the top of our wedge to the tip going straight down, because it's a little bit different than the inclined plane because both sides are angled. Okay, so it's going to be our length divided by our height. And the way this is standing up, it seems like this should be the width and this should be the height. But our length, the pointy end going up to the flat end, divided by the flat side, the side that you would hit. Okay? And again, that length is the perpendicular length. It's not the angled length. So the IMA of the wedge is going to be 10 divided by 3, which will be 3.3 repeating. And so we'll just round that off to 3.3 to 1. Right now here, we're looking at it takes 250 pounds of effort, and we're getting 700 pounds so if we look at the actual mechanical advantage of this one, we take the 700 divided by 250, and we get 2.8 to 1. So now we can figure out the efficiency of the wedge. By taking the actual mechanical advantage divided by the ideal mechanical advantage times 100. So that'll be our 2.8 divided by 3.33. Then we get 0.84. We multiply that times 100 and we get 84%. All right, now if we look at the screw, again, the formula should look the same. The ideal mechanical advantage is the distance effort over distance resistance. Okay, the distance effort, one rotation of the effort arm, which is the circumference. And then our resistance is the linear distance traveled during one rotation of the effort arm. And so we're looking at the pitch. We're looking at the pitch of these screws right here. Okay? So the circumference is 2 pi r divided by the pitch. Right. So I'm not worried about how wide the head is right here because, you know, if we're tightening a bolt or a screw, we're going to use a wrench or a screwdriver that has a better grip on it if it's a screw. But for a bolt like this, we're going to put a wrench on there. So the longer the wrench, the less effort it's going to take. So here we put an 8-inch long wrench on it, and we're going to assume that we're gripping it at the very end of the wrench. Okay, and you can hold the wrench in different places. So for our calculations, we're just going to assume that you are holding it, putting the effort at the very end of the 8-inch wrench. So that's going to be 2 times pi times 8 inches divided by 1 over 20. Okay, this is a 1/4 inch screw. It has, it's a non-coarse 20 pitch. So that's where we get 1/20. There's 20 of these threads in 1 inch. So if we counted up 1 inch, there'd be 20 threads. Okay. So we've got 1 divided by 20. So that comes out to 1005.31. And so we'll just round this off to 1 times 10 to the third, which is 1,000. The 10 to the third just means writing 3 zeros onto the 1 right there. So the ideal mechanical advantage is going to be about 1,000. All right, now if we're finding the actual mechanical advantage, we're putting 35 pounds of effort and getting 1,200 pounds of resistance. Okay, so we're tightening that bolt down pretty tight. So we take the resistance, which was 1,200 pounds, divided by the effort, which is 35, and we get about 34 to 1. So if we look at the percent efficiency, the actual mechanical advantage divided by the ideal mechanical advantage times 100. All right, so if we look at this, we can tell that this is going to be very inefficient. Okay, it's 3.4% efficient, which is good for a bolt or screw, because if we're tightening something in place, we want it to stay there. Okay, so we tighten it down. We don't want it coming loose, so we want that to be very low efficiency. All right, next lesson we will get to compound machines.